So then everything is fine. Then everything I can actually add as a total molarity. Why total molarity? Because again, the idea is that it really doesn't matter, okay, whether it is 2 or 3 or something like that. What matters is the addition of all the molarities. Okay, you can have just only one component, in the sense that only 2 is present. That is also fine. This is a generalized equation. Okay. Now if I have it, now you see I have basically used a relation of x1 with the molarity, then I can actually write what is the ln x1 readily. Okay. So ln x1 will be what? Ln x1 is ln this. Okay. It is ln a by b, which is ln a minus ln b. Ln a is 0, it is 1. So I have minus ln 1 plus m1 into m. Clear? Okay. Alright. Now where we left? Yeah. So basically this is one form of freezing point depression, in the sense that you can easily calculate it from here. Like T minus T star is the depression. Okay. So basically T star was the melting point, okay, for the pure solvent, and T is in the presence of the solid. Okay. So instead of using, so this is one form of the equation. Okay. But I don't want it to write it in terms of like x, but I want to use it in terms of molarity. Okay. So what I'm trying to say is that this is a final solution, but this is not a very useful solution. Okay. So I'll just, what I am going to do right now, I'm going back to this thing again, the ln x, okay, and use the ln x form here, okay, and then integrate it, so that I will get rid of all the x1s, or instead I will actually get everything in terms of small n, molarity. Okay, basically I am going back and rederiving it. Okay. So this is of course one relation, but I just don't want it in terms of x1. Okay, all I want is up to here it was okay. Okay, d ln x1 is this thing. Now I can directly use ln x1 is this. What will be d ln x1? Okay, very easy, right? So I'll have minus ln 1 plus 1 m. So the derivative is 1 divided by this, right? All right. And again, what is the variable here? Variable is small m, because how much amount of salt you add so that the freezing point depression changes. Okay. So derivative of this quantity, let me just write it. D of these things. Okay, is basically d of this thing. Okay, which is nothing but there is a minus sign. Okay. So I'll have 1 over 1 plus m1 m dm. It's a differential, not derivative. So yeah. Clear? Okay. Now I'll just write it there. Okay. So what I had is minus dm divided by 1 plus mm is m1. Okay. Is delta fusion h by RT square dV. Clear? Okay. So what we have finally is this thing, del T del n, okay, at constant pressure. So that should be, let's just have a look here. So when I take the derivative, okay, it is 1 over m1m. There will be 1 m1 also, because I am taking derivative of this thing. Let's say 1 plus ax. Okay. So it is basically 1 divided by 1 plus ax into a into dx. Right? So let me m1. Okay, fine. This is 1 plus m1. Okay. So what I will be left with is, if I just, let's say, write this thing del T del n, okay, I'll have M1, then this RT square comes here, RT square divided by delta function H bar, and then I have all this thing, 1 divided by 1 plus M. Clear? Alright. Yeah. So, now what I see here is that now I have a relation, okay, of the slope of a curve or something, how like t is changing with n. Okay. So that's what I wanted to get. There will be a minus sign also. Okay. Now usually I can see that it is basically a constant times a function of n, small n, right? And that constant we call as freezing point depression constant. Okay. So ideally the freezing point depression constant, okay, is defined as this quantity, which is negative of del T del M constant pressure when this molality tends to 0. If I just said M tends to 0, then basically I'm left with only this part, okay, which is nothing but M1 or T square divided by delta function H bar. Now one thing, when I wrote this RT square, okay, so just correct one thing, this will be actually T star square, okay, because this is for the pure solid, okay. So this will be actually T star square. Or actually, let me just a minute. We can actually keep this notation. Don't change it here, okay? Because I was just using it as a variable, right? Okay. Now here, why I am writing T star? Tell me. What is this approximation? When M tends to 0, then that thing. But M tends to 0 means what? It is kind of pure solvent. Then instead of T, I can just write it as a T star square. Now T star is it's a value, it's a fixed constant, right? So this thing is constant. Okay. So that we call as freezing point depression constant. Okay. Sometimes like, I mean it has many different notations also. Okay, let's not go into the details. Okay. So this is how we basically relate the freezing point depression. Okay. Now the elevation of boiling point is also the same. Exactly identically the similar derivation. But I'll just write the very first thing. Okay. You can just go through it. So we started there. Remember that freezing point depression. Okay. The solvent's chemical potential, okay, was identical in the solution phase or liquid phase as well as in the solid phase. In this case, I will equate it with the vapor phase because we are talking about elevation of boiling point, which boiling means actually it's an equilibrium between the liquid and the vapor, right? So all we will write is something like we'll start from here. I mean left hand side is the same, right? So mu1 in the liquid phase, okay, which is a function of temperature, pressure as well as the mole fraction, is identical to mu1 of the solvent, okay, in the vapor phase, which is a function of temperature and pressure. And we also know that most of the solutes are non-volatile, so this vapor is pure. Clear? Okay. And then we'll basically do all the maths. Okay. Only thing is that, remember last time we had here solid. Okay. And we were talking about freezing point depression. We were talking about like fusion process, right? So it took a minus sign. Here I don't need to do a minus sign because this is the final thing. And the liquid will be basically mu star liquid plus RTL and next one. That mu star liquid I will bring it here. So I'll have a mu vapor minus mu liquid. That is a boiling thing. So all this minus sign will disappear. Clear? Everything else will be same. Okay. So finally, I mean I can also define it similar thing like here for the elevation of boiling point. And we have a very similar thing here. So we call it as a boiling point elevation constant, okay, but we just write it as M1 or T star square divided by delta H bar, but this is the vaporization. Okay. Also, just to distinguish, these two T stars are different. This is basically T star for F, freezing point. This was for the boiling. Clear? Okay. But the derivation is the same, exactly same. Okay. Only thing is that just keep in mind that minus sign, there won't be any minus sign. Okay. Alright. Now, there could be other processes, okay, which are under colligative properties. Again, like for example, I mean, you can think of many different things. Okay. So we'll just discuss two more things. One is basically says solubility. Okay. Now, what is solubility? Solubility is how much like amount of a salt or something like that. Okay, and it comes into the solution. Okay. Now you know that it will be a function of temperature. Okay. Now, the problem we are discussing right now is something like, okay, suppose I have a salt here and I have liquid. Okay. So that basically the salt or something, okay, it comes into the solution. Okay. And when the equilibrium is reached, when actually basically the amount of salt which actually comes back to the solid form and which goes into the solid form is same, which means the solution has reached a saturated solution here, right? So for a saturated solution, now we can proceed and we can write the chemical potential. But this chemical potential is the chemical potential of the solute. Because when you talk about solubility, the solubility of a salt, which is the solute, right? So it's slightly different from the earlier two cases. Earlier two cases I was basically adding a salt, which is in the solution, okay? And then I'm comparing what happens to the freezing point and the boiling point of the solution with with comparison to the pure form of the solvent, right? So I was actually using x1 notation. Now I will use x2 notation. Okay. And again, it's the same thing. Okay. What is the same thing? Basically, the chemical potential of 2. Okay. In the solid. Okay. Which is a function of temperature and pressure should be identical. 2 means actually it is solute. Okay. Chemical potential of the solid in the liquid phase of the solution phase, okay, which is a function of temperature, pressure, as well as the mole fraction of solid. Okay, as simple as that. Now, here I can actually use the other equation for this. Mu2 is mu2 star plus NPTEL x2. Because we showed that if mu1 is equal to mu1 star plus NPTEL x1, I can also show it. Okay, for an ideal solution, again. Clear? So, the derivations are again same. So I'll write it as mu2 liquid star plus NPTEL x2. Clear? Okay. And then, just 1 minute. We can again write the same thing like solid minus liquid using a minus sign. Okay, that will be delta H fusion, same thing. Okay, so ultimately what I have is ln x2 is minus what we had, delta H bar divided by RT. Okay, and that was basically delta H fusion, right? Okay. Now again, don't get confused, this is with respect to the 2 in solid. Okay, it's not the fusion of the solvent. Okay. Earlier I was telling you how much heat you require per mole of water. Now I am taking actually per mole of sodium chloride. Okay, because I am talking about the solubility of sodium chloride. Okay, starting from mu2. Okay, although we are kind of using the same notation, but don't get confused. Okay, this is for the solid. Okay. Now again, what is delta H? Delta H is basically the reversible heat change at constant pressure, right? Now, if the pressure is constant, which means enthalpy is identical to heat change. All these things actually are keeping the pressure constant. Okay, if you see all the derivations. Okay, pressure we have not changed. Okay, otherwise you cannot establish the equilibrium. Okay, like if you remember that we are showing the mu versus T curve, right? So that is at a constant pressure. Or when we are showing the phase diagram, we drew a horizontal line at constant pressure how the freezing point is depression happening. Okay, so you have to define one parameter because pressure and temperature are the two parameters with which the Gibbs energy vary, right? Now, if I do that, okay, so here now you see that delta H is nothing but a reversible heat change if the pressure is constant. Okay, so I can right away actually use the concept of delta S fusion, which is the entropy change, because delta S is by definition is the reversible heat change divided by the temperature, right? So we can just write it as ln x2 is nothing but just making here the final. It is dln x2. Okay, and remember that we had some thing like 1 over t minus 1 over t star, right? This is after the integration. dln x2 was that, okay, and after the integration we have it, right? So what I'm going to write right now is that delta S is delta Q reversible by T, and delta Q reversible at constant pressure is nothing but delta H. So delta H by T is delta S. Okay. Now, which means I have to actually bring one T here. Okay. Now, there's also a minus sign. Okay. So, what I'm doing here, just follow carefully. Okay, what I'm doing. So, what I have here is 1 over T minus 1 over T star. Okay. So, I can write it as delta fusion. Again, there is a bar because it's all molar. Okay. Divided by R. So if I divide by T here, I have to multiply by T inside. Okay. So then I will have basically 1 minus just T star. Yeah. Right. Now, this has to be defined at a particular temperature. Okay, because it's an entropy change. Okay. Now, that temperature was saying that it is basically the T star temperature. Okay. At constant pressure, this is identical to delta H. I should actually always write it as reversible. Okay. Because Q, the heat change, can be reversible also. Because entropy is defined as a reversible heat change. Okay. It's a molar entropy, so it's a molar heat, it's an enthalpy. Enthalpy I never write as reversible because enthalpy is a state function. Clear? Okay, so I'm not using this notation. So now we compare. So basically we said we are basically multiplying by T star here. Okay, so it will be T star by T. It will be 1, but now I'm actually switching sign because I have inserted the minus sign. So I'm just writing it as 1 minus, okay, T star divided by T. Clear? Okay. So what we create is that x2 has some kind of exponential relation, right? It will be something e to the power delta fusion by r, whatever, 1 minus T star by T. Okay. So if you want to plot it, right, how basically with respect to temperature, the x2 changes. Again, x2 is mole fraction of solute. Okay. What could be the maximum value of mole fraction? It is 1. So it will go from 0 to 1. Okay, so this is suppose the maximum value. Okay. And the rise will be something like this, okay, with respect to temperature. And what is this point? When actually T is equal to T star. Okay. This basically tells you how the solubility is changing. Okay. But which is very interesting. What was T star? T star was basically corresponding to the fusion process, which is basically the melting, right? So when what I'm saying here, suppose I have a solid, okay, and then I am actually starting from with a temperature which is actually below the freezing point of the solid, okay, or the fusion point of the solid. Okay, and then if I elevate the temperature, when it reaches basically the T star, okay, so then I'll have basically have this entire solid basically melts. Okay, because now it is the pure solute. Okay, so but in between I can actually explain the variation. Okay, but again this is very ideal solution, and most of the solution doesn't actually show this kind of behavior. The reason is, in real life you have many different things. For example, if I add sodium chloride and some other salt, okay, there are in water particularly, there will be hydrogen bonding. The interactions will be very, very different. Okay, and see here, it does not depend on whether it is a I mean, it will depend on the salt, because actually, as long as the delta S for the two salts are same, okay, it will behave identically. If they are different, they will behave differently. But suppose if I take two substances for which delta S fusion is same, still they can behave very differently because of very molecular level interaction. Okay, so that again we are not including here. Okay, so the last thing which we'll discuss, okay, is the osmotic pressure. How we can actually define the osmotic pressure. Now all these things, if you follow, like freezing point, depression, elevation of boiling point, everything, okay, are all connected. That the chemical potential of one component that is present in different phases are same. That is the starting point. Okay. Now, what is osmosis? All of you know that if I have a semi-permeable membrane, right? So then I can have only the solvent flowing through it, not the solute. Okay. And a particular setup can be like this. Let's say I have suppose water, okay, and then what I did is that I suppose kept something, okay, which is made up of a semi-permeable membrane. Now semi-permeable with respect to what? Let's say water. Okay, so I have water here, suppose, and here suppose I have, the classic example was basically sugar solution. Okay, sugar or salt doesn't matter. Okay, let's say sugar plus water. Okay. Now what will happen, think about it, if I just start, okay, with the sugar solution with the same level, okay, water will actually diffuse into it. I mean, osmosis is nothing but actually diffusion of one component, which is the X1 component. Okay, so they will diffuse and ultimately an equilibrium will come. Okay, and suppose at the equilibrium, what will happen, you will observe that this level has increased. Why? Because actually water has gone itself. Okay. So I have sugar and water here, I have water here. So sugar is basically the component 2. Now what I should look at? I should look at the component 1, because that is present everywhere. And as usual, the component 1's chemical potential will be identical here and here. That's it. Okay. Inside the sugar solution as well as here. Okay. Now there is an interesting thing. What is the interesting thing? The interesting thing is that, see, here there is a difference in pressure because there is a difference in water level. Okay, so that's why Van Hoff thought that what is the driving force here is actually can be related to the pressure, because any height of the water level can be related to H rho g, which is a pressure, right? So he said that there is some kind of pressure which is defined as osmotic pressure. Okay, and what is this pressure? If I do not have it, there is some pressure which is the atmospheric pressure, which actually I am writing it as something like something P. Okay, but due to this increase of height, there is an extra pressure which I am writing it as a pi plus P. Okay, because P is always acting, but this is the extra amount. Okay, pressure. So that will be same. Which means, suppose like at a same level, like like chemical potential, of course, will depend on a particular species. Okay, which is a function of temperature and pressure. In this case, I'm not talking about temperature. Earlier 3 examples I was talking about temperature, how the temperature changes, right? In this case, temperature is same, but there is a pressure difference. So the colligative property can also arise because of pressure, which makes sense because the Gibbs free energy or the chemical potential, the natural variables are temperature and pressure, right? So in this case, actually, it is arising because of the pressure difference. Okay. Now again, let us just try to follow somewhat similar notation. Okay. So what I'm trying to say here is that if I want to just write a very simple equation, okay, for the osmotic pressure, so I should write it as, say, mu. Okay, in the two phases should be identical. Okay, I'm just writing it as a mu1. Okay, 1 means water. Okay, at a fixed temperature. Okay, at a pressure which is P plus pi, which means actually chemical potential inside. Okay, but when I'm considering a chemical potential inside of water, okay, that is also dependent on the mole fraction of water, because this is pure water, but this is not pure water. Clear? Okay. Now when you measure the chemical potential or anything, you actually think about a one particular level. Like say this level, because the pressure will change. Right? Now this level, suppose I am assuming that pressure working is basically P. Okay, which is of course will be more than atmospheric pressure, because atmospheric pressure is at this level, but there is also water height. But here it is not only P, it is basically P plus pi. That is the entire concept. Okay, at some height, okay, the pure water is experiencing a pressure P, but the water inside, which is actually in the solution, is experiencing a more pressure. Of course, this extra thing will be proportional to this height. Okay. So let us not actually convert it to height. We will just keep it as a pressure thing. But you can always like convert it to the, because it's very straightforward. It's just H rho G. Okay. Now let us do it. So this is also dependent on the mole fraction, right? Is identical to the chemical potential, which is a function of temperature and pressure in the other side, but that is actually the pure water. Okay, that is mu star. Now we are basically done. Okay, so what I'll write, I'll just write it as a mu star plus those things. Okay, but there is an interesting thing. I'll come to it in a minute. Okay, so I have basically mu star, mu1 star, which is a function of temperature T plus phi. Okay, and I'll have minus. I can actually keep the minus RTLNX on the other side, and I'll have mu star TP is RTLNX x1. Okay. Now look at it. Like this is slightly different now. Okay. So earlier case, what we had is that we were supposed writing mu1, same temperature, same pressure, but in different phases. Like one was in solid phase, one was in liquid phase. Here actually both in liquid phase. Okay. Difference is here, P plus pi and P. Clear? I mean, in our original notation, this is basically mu1 liquid. This side also mu1 liquid. Okay, this is mu1 liquid. This is also mu1 liquid. Something like that. Clear? So the difference is coming in pressure. Now, what I have to do is the difference in the chemical potential, which is difference in the Gibbs free energy. How Gibbs free energy varies with pressure? So I know that dg is basically minus hdt plus vdp, but T is constant. This is T, this is T. So it is nothing but vdp. But it is not vdp, it is v bar dp, because it's a molar Gibbs free energy. Okay. So this difference is nothing but vdp. Okay. So I can write this is nothing but v bar dp. Okay. Where the pressure change from P to P plus pi. As simple as that. Clear? Because chemical potential difference is nothing but the Gibbs free energy difference per unit mole. This is arising because of a pressure difference, and I know that the change in chemical potential, Gibbs free energy is this. Okay, or the d mu is nothing but all the molar quantities. Okay, for constant temperature, I will have only the vdp term. Clear? Okay, so this is nothing but RTLNX, or I was writing x1 probably. Okay. And now we can, this is just straightforward. Okay, so what we have is v bar pi. Let us just write it. Okay. So just to like keep the same notation, I can write it as a V star pi, meaning it's the molar volume of pure liquid. I mean pure water. Okay, because it's a difference of the stars. Okay, so I'm just using the same notation. Okay. So what we have here is RTL and X1. Okay, but again, I mean this is a correct form. Like let's just write it here. But we can make some approximation right now. RTL and X1 is nothing but V bar star into pi. Right? So now let us see what we can do. Okay, again X1, instead we can actually add molarity or something like that. Okay, in this case usually people write in terms of the molar concentration. Okay, like suppose I have water, okay, and I'm having some tube with a parchment paper or whatever, and I'm adding a solution, okay, a concentrated solution of sugar or whatever. Okay, what is the concentration? Okay. Now, if I know the concentration, can I actually report what is the osmotic pressure? Okay. So all I have to do is somehow cleverly connect the X1 with just concentration. Okay. So again, so let us just write the RTK. Now, what is ln X1? ln X1 is nothing but ln 1 minus X2. Right? As simple as that. Which we can approximate again. Okay. As X2, because usually the X2 is small. Even if you take very concentrated, but still the water is the major one, I mean the bulk phase, right? So this X2 is what? X2 is basically mole fraction, which is basically N2 divided by N1 plus N2. Okay, which you can again further approximate. Since N1 is much larger than N2, it is N2 by N1. Okay, now I can just quickly write. What I got is basically an expression for pi. Pi will be RT into N2 by N1. Okay, N2. Yeah. Just a moment. Yeah. Now what is V star? Molar volume of the solvent. Can you just when I was writing it, you can actually write it as instead of V, you can write it as V1 because it's for 1. Okay, not for 2. Okay. So where we wrote as basically mu1 star P plus 5 minus mu1 star P. There actually we wrote it as a VDP, but better actually write it as a V1 star dP. Okay, just for the 1-2 notation. Okay. Now think about it. What is this? V1 star, molar volume, times the number of moles. It is basically the volume. Okay, the total volume. So it is basically RT N2 by the total volume. Okay, total volume of what? Of the pure thing. Okay. Now when I am adding N2, the volume change is small. So I can assume that this V star is roughly the total volume. Because I had a water, okay, I am adding sugar. Of course there will be some volume change, but I can ignore that. I can think that this V star is nothing but basically the V total. Okay. And what is this N2 by V total? N2 is the number of moles divided by volume. It is the molar concentration. Okay, of the solid. Okay, so this is nothing but which we write it as C or like C bar or whatever. Okay, CR. So we got a very compact form. Then the osmotic pressure is nothing but the molar concentration of the solid times RT. Okay, this is also known as a Van 't Hoff equation. But now in literature there are many Van 't Hoff equations. Okay, so this is Van 't Hoff equation for osmotic pressure. Okay, well, let me summarize what we just did. Okay, in today's class. So basically we talked about the colligative properties which arise. Okay, due to the change in chemical potential. Okay, going from a pure form to a form where actually I am adding a second component. Okay, And then the approach is the same. What is the approach? Like, I have three phases, okay, solid, liquid and gas, okay, or vapor. And then initially what we said is that we are basically adding a salt or solute, okay, whatever it is, of the form of the solute, which actually goes only into the solution phase. And the solid for the solvent is pure, and the vapor is also purely solvent, because the solute is non-volatile, as well as when it freezes, it actually separates from the pure solvent. Okay. With that assumption, we said that we can actually get an expression for the freezing point depression as well as elevation of the boiling point, which I did not show the elevation of the boiling point, but the derivation is the same. Okay. We can write an expression in terms of X1, which is mole fraction, or molality equivalently. And for the molality expression, we can get a combination of terms which is a constant, which we call as a freezing point depression constant. Okay. Similarly, we can call about a elevation, boiling point elevation constant. Okay. And then we talked about that there is something called solubility that also can be explained in the same way. Okay. And then there is a thing called osmosis. Okay. Which again we can relate to the same way, that the chemical potential of one of the constituent, okay, actually in any constituent should be same everywhere. But in this case, actually, you know that outside there is no sugar, like the sugar cannot penetrate, because that's why it is a semi-permeable membrane. Okay, so that's why the semi word, right? So in this case, that's why I took water. Okay, but then the beauty with osmotic pressure is that the difference from the earlier cases was basically we are talking in terms of the temperature. Here actually temperature is fixed, but the pressure is changing. Okay. And there we use basically the standard Gibbs free energy change, how basically the pressure variation happens, and by using some approximation, assuming that the number of moles of the solute is much less compared with the solvent, okay, we can get a very compact equation. Okay, so these are all known as colligative properties, and all we derived for ideal solution. In the sense, again going back, that the pressure was basically falling linearly, okay, with mole fraction. But we know that there will be deviations for different substances, okay, and in reality nothing behaves ideally, okay. So all these derivations are only true for ideal solution. Secondly, there was one more assumption throughout, that the solute we are adding is non-volatile. Okay. So the things which we have to take care of now is basically if we have solutes which are volatile, okay, or other things like, say for example, if I have a solute and a solvent, if they freeze together, okay, all these things, all these assumptions which we make, as well as much later, okay, we will also have to understand what happens if they do not behave ideally, what happens for a real life situation, or what happens for a non-ideal solution. Okay, these are the things that we have to check, because non-ideal solutions are important, because when we start about electrochemistry, it involves all ions. The moment you add ions, it is much deviated from your ideal behavior. Okay, because the ionic interactions are dominant there. Okay, all right, we'll stop here.